These examples are relating to differentiation of the log function. So our basic function here, if f of x is equal to log to the base e of x, then f dash of x is equal to 1 over x. As with the exponential function, just differentiating that is not very exciting. So we combine the log function with other functions. So we're generally speaking differentiating a composite with the log function. So if we have g of x equaling log to the base e of f of x, then this is a composite function, and our derived function is 1 over f of x, differentiating the log part, the outside part, multiplied by f dash of x, which is the inside, and this is generally simplified to f dash x over f of x. And that's going to be a very important pattern for you to recognise later on when we are integrating these functions. A couple of examples to illustrate how we go about differentiating these functions. The first one, f of x is log to the base e of 2x cubed minus 4. Now we can differentiate this one straight away. We don't have to do any rearrangement of it at all. F dash x, the outside function of the composition is the log part. So the derivative of that is 1 over 2x cubed minus 4. And then the derivative of the inside function is the 2x cubed minus 4, which goes to 6x. Then we can tidy up what it looks like, and we get 6x over 2x cubed minus 4. The second type of example, if f of x equals log to the base e of x squared plus 2 all cubed, what we actually have here is a 3-level composition. We've got the outside function, which is the log function. The next level of function is the cubed function, and then the x squared plus 2 is the very innermost function. So when we come to differentiate this, we've got the log function, which gives us 1 over x squared plus 2 all cubed. Then we have to multiply by the derivative of this x squared plus 2 all to the power of 3, which is a composite function. So we have to differentiate it as a composite function, the outside coming first, so it's 3x squared plus 2 all squared, and then not forgetting to differentiate the inside part of that, which is 2x. And then we can just tidy this up a little bit. 3 times 2 is 6. Bring the x to the front, x squared plus 2 all squared, and then the denominator is x squared plus 2 all cubed. So we had that 3 levels when we differentiated what was inside the log function. It was in itself a composite function, so we had to differentiate it as such. A third type of example you might get, f of x equals log 1 over x squared. And just a reminder here that log x written like that means the same as log to the base e of x. And you may well get both forms of this in the questions. Now this question here, we've got log of 1 over x squared. Now we know that we can't differentiate 1 over x squared when it looks like that, so we have to do some rearrangement to this first and make it x to the negative 2. Now we're ready to differentiate it. f dash of x is equal to 1 over x to the negative 2 from the log part of it, multiplied by the derivative of that, which is negative 2 x to the negative 3. And then we could tidy that up a bit if we wished. We've got minus 2 x to the negative 3 over x to the negative 2. And we could even go further and put it back with positive indices. So the x to the negative 3 comes to the bottom, the x to the negative 2 goes to the top, so we've got negative 2 x squared over x cubed, and we could simplify that one step further, negative 2 over x. Leaving it as it was originally would be fine, but it can be simplified down as negative 2 over x. And certainly if you were wanting to go on and do something with this derivative, you would want it in its simplest form. Just a reminder here about how I'm setting these things out. It's very important that you've got your function specified, and then when you find the derivative, you change your left hand side to f dash x. And especially important when you're actually doing some rearrangement and simplification, and then saying your f dash x there.